So let's start. Any question about last lesson material? Everything's clear? Okay. So we did a little bit of the theory about the autoregressive processes. We presented the moments of an autoregressive process of order one. Well, we derived everything for the order one. Then for P, I gave you some information. Of course, we didn't derive everything just because it's cumbersome. It's not difficult, it's just cumbersome. We presented the partial autocorrelation function. So we already knew the autocorrelation function of a stationary process, and we presented the partial autocorrelation function, which in some way neutralized the autocorrelation functions for like transitive effects. Let's call it that way. So we see through the partial autocorrelation function if there is a direct link between the observation at times t and the observation at times t minus h, for example. Okay. And then I showed you how it looks like the general autocorrelation function and partial autocorrelation function of any ARP process. Okay, so basically the autocorrelation function of ARP process goes to zero gradually, but geometrically fast, so relatively quickly. Of course, the more persistent the regressive process is, the slower is the convergence to zero. And because we saw that actually autoregressive process can produce arbitrary long memory. So they're classified as short memory processes in theory, but we saw that the closer we get to having a so-called unit root, so one of the solution of the characteristic equation being close to one, then the more it will behave closely to an integrated process, which is non-stationary. So an ARP process can generate a lot of persistence, okay? And instead, the partial autocorrelation function of an ARP process is different than zero just for the first P lags, okay? If you remember, we also simulated some processes. So for example, last time we simulated, I think this is an ARP of order 2. No, this was, okay, this was the real one. So the real time series. Okay, this was, for example, is, oops, what happened? So, for example, this was the partial autocorrelation function of AR1. So only the first autocorrelation is different than zero. This is, of course, very close to the theoretical one because I sample a very long time series. It was like 10,000 observations with phi equal to 0.9, okay? So this is the autocorrelation function. It goes to zero. In this case, it's an AR1, so it goes to zero in a very ordered way, in a very smooth way. In general, an ARP process doesn't have to be so smooth. It can go up and down. It can actually change the sign every time. For example, if we use a negative coefficient also for the AR1, then we get something that changes sign every time. But the concept doesn't matter if it jumps up and down and so on. The concept is that it goes to zero gradually at a geometric pace, okay? So that's a way we can use to find out if some data were generated by an autoregressive process. But even more interestingly, a partial autocorrelation function of an ARP process is different than zero just for the first P legs. Okay, in this case, this is AR1, so we have just the first leg, which is different than zero. Okay, and a simple way to remember that is that it's ARP, and you find the P on the P partial correlation function. That's the way you can simply memorize that. Because that's, of course, what you're going to be using for identifying the ARMA models from time series, from real time series, okay? And then we saw this was a real time series. This is how we ended up our lesson last time. So this is the log differential, seasonally differential time series air passengers. Okay, so we took the log to fix the non-stationarity in invariance. We took the seasonal difference to fix both the seasonality, which is a form of a non-stationarity usually, and also taking any difference will kill also the possible trend. So this also kills the trend, and indeed this is the time. We could think this of as if it's generated by a stationary process. Okay, and so now it's meaningful to go and look at the autocorrelation function, and we did that. Well, this is well, this was just a simulated AR2. I don't know why it's there. I remember the sequence of things we did yesterday. And this, okay, this is also a simulated AR2. As I told you, a simulated, an AR2 process, for example, can generate also cycles in the autocorrelation function. It doesn't matter. The importance is that this goes to zero gradually. So this is very persistent. Probably I simulated a very persistent AR2. Right. But anyway. And this is the partial autocorrelation function of the simulated AR2. You see the first one, the first lag is out, the second lag is out, and all the other ones are close to zero. Of course, there's some sampling volatility, so uncertainty. But then we looked at the autocorrelation function and partial autocorrelation function of the differentiated log airline. And this looks like this could be generated by an autoregressive process. This is the ACF, it goes to zero gradually. And the PACF, well, we see these two being quite different than zero. Then it goes to zero, and then, okay, there's something more here. Maybe we will learn what this is possible. What's the effect of that it's possibly causing this extra autocorrelation here? But if we look at the first year, it looks pretty much like an AR2 process. And indeed, if you remember, we ended up the lesson by, well, this is the version of the ACF and PACF of the forecast package. It's just a little bit better. And then we fitted an ARIMA. If you remember, we fitted our first ARIMA. Actually, the MA part we don't know yet. So we just fit an AR2 process to a seasonally differentiated time series after having taken the log. So the lambda equal to zero is the log. And we included a constant, and we spent some time last time to give you the interpretation of what's a constant. Well, the constant, the role of the constant depends on if you have taken some difference or not. If you didn't take any difference, the constant is, we saw, proportional to the mean. Okay, it's not the mean, but it's proportional to the mean. I gave you the formula to move from the intercept or constant, whatever you want to call it, to the mean and back. Okay, but if we have a constant after a difference, well, that means that we have a drift. What's a drift? Well, it's a linear trend at the end of the day. So we have a linear trend. So if there is non-zero constant or intercept in the model after taking the difference, then it means we're leaving the possibility of having a drift, which is good for this time series because it's, of course, it's drifting. It's got a positive trend. Okay. And we ended up indeed with, well, this was the model, the estimated model. And we ended up with producing forecast. Well, the forecast function of the forecast package is very handy because it does everything. It takes the model. The model contains also the past data, so it's able to use the model to produce the forecast and actually also produce prediction interval. Last time I explained you the difference between prediction intervals and confidence intervals. These are prediction intervals, okay? which are the intervals usually you're interested in, okay? Something that it's very popular in forecasting, it's been popular the last 10 years maybe, but it's getting more and more popular because of what we discussed in the first lessons. So the fact that loss functions may be different than just the quadratic loss function is forecasting probability distribution. So we know if we predict the future of a time series by just point forecasting, so giving numbers for the future, we're 100% sure that we're going to miss it, okay? It's just the way it is. If it's a continuous random variable, whatever number I'm going to shoot, then the real number will be different because it's continuous, okay? But so it's like say, what's the probability to get any point in this table if I touch it with a zero-dimensional pen? It's zero, whatever point you choose, okay? Because it's continuous, so there is no problem. The same is here. So usually predicting probabilities, it's more informative. Of course, you can, if you have a probability prediction, of course, you can apply your loss function even after having built the model, okay? You don't have to specify the loss function before the model because the model is a model that is going to give you the future distribution of the data. What's the future distribution of this data? Okay, when we apply ARMA models, we usually assume Gaussianity, okay? But we are modeling the log of the data, not the data. So actually, here we don't have Gaussianity. What do we have? What do we have if I take the exponential of the Gaussian distribution? Remember that? It's a log normal distribution. So we are actually assuming that this data are log normal, okay? So which is the distribution which is asymmetric? It's fine that it's asymmetric because it's only positive data. You know, if it's positive data, it's really, it would be strange to have a perfectly symmetric distribution because of course the zero is a bound. Anyway, so if we want, so well, here we have prediction intervals. We saw that actually have like 80% and I think 90% by default prediction intervals. But actually, if we have the mean and we have the variance, we also have the mean and the variance. We have the whole distribution because we know, or we are assuming that the data are, well, normal after the log. So the original data are conditionally log normal. So actually, we do have in a statistical model the whole distribution of future data. Of course, I pay more attention to the point prediction. So, but there are also ways to verify if your predictive distribution, that's the name of it, it's a good approximation of the real distribution of future data. Of course, you can do that by, for example, cross-validation. And of course, you have to compare the whole distribution of data and not just the mean. But anyway, this is just to tell you, point prediction is not the only thing you can do. You can also predict the whole distribution of future data. And actually, by statistical model, that's what you're doing, even if you sometimes just concentrate on the mean, the conditional mean. One other thing, last time I was already charging you with too many pieces of information, so I left out a parameter of the ARIMA function, if you remember. Well, here's the lambda. The lambda defines the transformation, the Box-Cox transformation, which to get the log, we have to fix lambda equal to 0. But then just after that, we have this bias adjustment. Any clue of what that thing is? Default is false. But of course, we can turn this true. Why bias? Okay. I already gave you some clue when talking about predictions, okay? So what we are doing right now by this model, of course, any other model would be the same. So we're interested in something we call YT, but actually we're predicting something that we can call, I don't know, WT, which is the log of YT, right? So this is our air passengers, okay? But we're actually building our ARIMA model. Well, the AMA part we haven't defined yet. That's what we're going to do today. But I want to tell you these things now that you're fresh, then, which is better than at the end of the lesson they're not so fresh anymore. But anyway, so we're actually predicting this using an ARIMA model, but it doesn't matter. We're predicting this, and we're building something that we know. I mean, the optimal predictor, if my assumptions are correct, so Gaussianity and so on, we're predicting the future of this time series given the past, or maybe if we call n the last observation, maybe we can say I'm predicting W n plus, I don't know, H is the horizon, so the forecast horizon, given all the information, all the past information. Of course, I can write here, I can write W or write Y, and it doesn't change. Why doesn't it change? Because W is a one-to-one transformation of Y. So knowing one, I mean, this is the condition. This is not the linear prediction. If it was the linear prediction, then of course the information is different. If I do it knowing W or Y. But this is not a linear prediction. This is a conditional expectation. And so actually I'm conditioning to all the information that is available up to time n. If you know some probability, this is called the filtration of the process. But it doesn't really matter if I call the W or Y as soon as I can get one from the other one. Okay, it's the same information. Okay? If there is lots of information, then that counts. But if I take like a monotonic transformation like the log, then the information I'm conditioning to doesn't really change. Okay. Okay, so what we are doing is we're computing the conditional expectation using the ARMA model. But we're not interested in W, we're interested in Y. And so we can call this W hat n plus h given n. But we are actually interested in y n plus h given n. So what's this? Well, it's not just the exponential that what we know is that it's not the exponential because the box-Cox transforms, they're not linear transformation, and nonlinear transformation of the expectation are not the expectation of the linear transformation. So what I know is that this is not true if this is not true if I want to predict using the conditional. Sorry. So if I am predicting using the conditional expectation, well, this is not true. Okay. But we do it anyway. We do it anyway. And in this case is when I say I don't want any bias adjustment. So the bias adjustment parameter there is asking, do you want me to produce the correct conditional distribution or not? So what's the correct conditional distribution? Well, it depends on two things, on the transformation you take, and we have the whole set of box-Cox transformation, even though the most popular is, of course, the logarithm. And it depends on the distribution of the data, okay? So if we assume that, well, the omega is well approximated by a Gaussian distribution, and we took the log, then, as I told you, if I take the exponential and to get y, then have the log normal distribution, okay? And I don't know if you ever seen the log normal distribution, but anyway, you can check it on Wikipedia. So under Gaussianity of WT and log transform, we have that the conditional distribution of the log normal is equal to the exponential of the mean of the normal plus 1/2, so 1/2 of the variance, which is in this case is the prediction variance. Okay. The problem is that this variance is also estimated because it's related to the variance of the innovation, so of the epsilons in the model, which we also have to estimate. So this is usually substituted also with, so this is okay. So this is estimated. So if we knew the exact sigma square here, then this would have been a better prediction because it would be the conditional expectation. The problem is that we don't know this, and we substituted with an estimation of it, and so this is anyway going to be approximate, and something it's not a better approximation than just dilating this part here. And usually this is much smaller than this one in a real-time series, okay? So that's why usually we tend to predict just using this part and not adding that part there, okay? And then there is also another reason. So why are we predicting with conditional expectation? Well, just because we are using usually, if we don't say anything, we use a quadratic loss function, right? What if you use like the absolute value instead of the quadratic loss function? We saw that if I decide to predict with the a loss function, which is the absolute value, the best predictor is not the conditional mean, but it's conditional median, okay? And the conditional median actually is, we can say, equivariant to monotonic transformation. So the exponential of the median is still the median of the new distribution. So, and if the distribution is symmetric, and we are assuming Gaussianity for W there, the mean and the median are actually the same thing. So we can, of course, if I just take the explanation, this is not going to be the conditional expectation of Y, but it's going to be the conditional median of Y. So we have still some form of optimality, even if we don't correct for this bias term, okay? Of course, the bias term changes according to the Box-Cox that we have chosen, and the forecast has all the right correction, if we want to. Otherwise, we're still predicting with a quantile, so with a median, which is still a good predictor, meaning that it minimizes the absolute error instead of the mean square error. Okay. So is that clear? So as you see, I want you to get more insight on what you are doing when we are predicting this way, so forecasting, but also in any other model you've been predicting using machine learning model, statistical model, whatever. You have to know what you're doing. Okay, I think we try to give you some more information to know what you're doing when you're predicting something. Okay, so if you say true in the bias adjust parameter, it will just put the estimated variance of the prediction errors. Okay. Otherwise, we'll just take the exponential. So this will be. Mm-hmm. Because of Jens inequality, Jensen inequality, sorry. It tells you that the condition, for example, if you take the exponential is a concave function. In that case, the expectation of the transformation is smaller than the transformation of the expectation. Okay, so you have to add something to make it larger. Okay. And in the Gaussian case, we know exactly what that number is, but that's in general. So if you look in Wikipedia, Jensen inequality, you will see the only transformation that leaves the expectation equivariant is the linear transformation. Okay, so we know that the expectation is linear. What does that mean? That I can take a linear function of the expectation or the expectation of the linear function, I get the same result. For nonlinear transformation, the expectation it changes, okay? But that doesn't happen with quantized, and of course, the median is also quantized. If you take an invertible transformation, monotonic transformation, for example. Monotonic transformation, they preserve all the quantized. Okay? So the new word has the quantized, they're just the linear transformation, or also the linear transformation of the starting world. Okay. Good. So let's go on with so how do we have to expand now the ARMA models? First of all, we have to learn the MA part. The MA part, which is for moving average. Okay, moving average is not a very intelligent name because it's not a moving average. It's actually a moving moving linear combination, I would call it. But I mean, that's the name. It's caps. We have to keep it. So, so moving linear combination would be a better name. So, an AMAQ process is a process where our data are generated by just a linear combination of a present and past white noise. So epsilon is a white noise sequence. And I just take a linear combination of the last, of the present white noise and the last Q white noise, okay? It's actually, you can see it from here, and of course, it's very simple then to derive also, for example, the autocorrelation function. It's a process that can only have a short memory. So the longest memory you can get from here is Q logs. Because here, you know, if I don't take any delay, I get the white noise, which doesn't have any linear memory of the past. Of course, the more lagged white noise I have, the more memory I introduce, because the shock that happened last time is still have an effect today. And the shock that I saw I don't know, logs ago, Q periods ago, is still having an effect today. But before that, that's all forgot, okay? So they're very short memory processes. And what does that mean? That when we use them for forecasting, they will adjust the very first predictions we're going to produce, but then for longer predictions. So from the prediction of Q plus 1 period ahead, it will be non-influential, the effect of the MA part. So just a very short memory. And indeed, okay, these processes are always stationary. When I say stationary, we're speaking about weakly stationarity. Okay? Again, it's simple to see it because I mean, what does it mean stationary? It means that the mean is constant. Okay, here the mean is 0, it's clear. If I add the intercept, of course, we can add the intercept. In this case, the intercept is the mean, because of course, they all have mean 0. So if I add an intercept, we can do it. Well, we can do it afterwards. The intercept in this case is the mean. No intercept, 0 mean, okay? The mean is simple to see it's 0 because we are taking the mean of everything that has mean 0. So the mean is constant over time. What about the variance? Well, the variance is also very simple because they're all uncorrelated. They're white noise. So by definition, they are not correlated. And so the variance of YT is just, so the variance of epsilon plus the square of this θ1, well, the square, well, because the variance takes the square, of course. And again, the variance multiplied by the variance of epsilon. And then we have the square of θ2, and then again, the variance of epsilon up to, so to T minus Q. So Q period, it doesn't depend on T, it's T independent, so stationarity is there. And again, of course, we should also compute the autocovariance. And the autocovariance is also simple to compute because suppose you want to compute the covariance of YT with YT minus 1. Well, then you just have to rewrite this log. And of course, everything that will survive to the expectation are the times in which epsilon encounters an epsilon with the same index, okay? We can compute it for example, for let's compute it for everything for example, MA2, so we don't have to write that much. Actually, MA2 with intercept. So Hmm. Okay. So the expectation, we said it's very simple. It's just k because all the other expectation they are equal to 0. What about the variance? The variance of yt. Well, the mean is k, so actually this is just equal to yt minus k, which is the mean. We just saw that it's the mean. And so it's just the square of this under expectation. But these are all non-correlated, as I said. So actually we have well, we have just a here too, sorry. Okay. Because I get the variance of epsilon, then I get the square of theta 1 times the variance of epsilon plus theta 2, the square of the, I mean, the variance of epsilon. And of course, I would have, I'm taking the square, so I should have also the double products, but, under expectation, if the index of the white noise is not the same, it's going to be 0 because the autocorrelation is 0, the autocovariance is 0. So all the cross product are 0. Okay, and so the variance is just. Is that clear? Should I make more passages? Should I? Okay. Just ask. I don't want to. I never know if you're. It's going to be too boring or too less detailed. So for example, let's compute in general the the variance. Let's start with the variance. I don't want to make things too complicated. So if I take this and bring in the other side, all that will remain is the epsilons. So it's the expectation of epsilon t plus theta epsilon t minus 1, theta 2, epsilon t minus 2, at the square. Okay. So I have to take the squares. So I have like the square of epsilon t, then I have the square of theta 1 times epsilon t minus 1, the square of theta 2 times the square of t minus 2, and then I have the double product of all the cross products, right? Well, I sample theta 2 okay. Now we take all the expectations. So the expectation of this is just the variance of epsilon. Okay. So I take the expectation. Of course, this gets out of the expectation because it's just a parameter. So the random variable is there. And again, I have so theta 1 squared times the variance again of the white noise. Same thing here. So I have theta 2 squared plus times the variance of the white noise. And all the rest goes to 0 because if I take the expectation here, this is white noise. The autocovariance of white noise is 0. So all the cross product here, the expectation is 0. And so I get the result I just showed you. Okay. What about the lag 1 autocovariance? So Again, I can substitute the definition of yt minus k, which is just the sum of the white noises. Then I have the lagged version, which is yt minus 1 plus theta 1 epsilon t minus 2 plus theta 2 epsilon t minus 3. Again, we can ignore all the cross product. I mean, when I mean cross product, I mean when the index of the epsilon are different, because when the index of the product of two epsilon is different, when I take the expectation, that goes to 0 because of the non-correlation of the white noise. So I just have to isolate the times in which epsilon multiplies an epsilon with the same indexing. Okay. So for example, this with this is going to be important. It survives because it's the square. Now it gets the square of the epsilon. This is important with this one. And all the other ones will just disappear, okay? Because of correlation being 0. So the only ones that survive are theta 1 times the expectation of epsilon t minus 1 square, and then theta 2, actually theta 1 times theta 2 times the expectation of yt minus 2 square, and all the rest goes to 0. Okay. So the first leg autocorrelation function is just something like this. Okay? It's just an exercise. Of course, I don't want you to compute this for every MA process. Then, of course, this is MA2, so we still have a non-zero autocovariance at lag 2. Let's try to compute this. Again, we can do the same game where we substitute yt with epsilon t plus theta 1 epsilon t minus 1 plus theta 2 epsilon t minus 2. Multiple, now I have to lag 2 times, so I have epsilon t minus 2 plus theta 1 epsilon t minus 3 plus theta 2 epsilon t minus 4. What survives here is just this pair here, okay? That's the only surviving part. So it's theta 2 times the square of sigma, okay? Oh, of course, starting from, let's say, third leg and larger, if you delay this one more time, you will see there is no epsilon that encounters another epsilon with the same index, okay? Because they get too far away from each other. And so this is going to be 0. So that's what I meant by telling you it's a process that has only very short linear memory. The longest memory we get is Q periods. Starting from Q plus 1 legs, there is no memory. Okay? Linear memory. Okay? So we've seen that in a linear model, so we do linear prediction, linear model, and so on. All that counts is just correlation. Okay? And we saw this of covariance, correlation are just the same thing. We scale. Okay? And we see the maximal lag of non-zero correlation we get is the order of the MA process, so the Q. So it means I can exploit just the last few observations to predict the future. All there is other than that, it's not that interesting anymore. Yeah, because there is no memory of what happened before. So very short memory processes, but still useful. And what about the partial autocorrelation function? Well, the partial autocorrelation function is not so straightforward to compute, but I will tell you that it goes to zero gradually in an exponentially fast fashion, okay? So it's kind of the opposite that we see in the autoregressive process. So for an autoregressive process, we have the partial autocorrelation function that is different than zero up to log p, while the autocorrelation function goes to zero gradually in a geometric fast way. For an A process, it's the opposite. So you have the autocorrelation function that is different than zero up to q, so the log q, and then it's zero from log q plus 1 on. And the partial autocorrelation function goes to zero gradually, okay? And that's basically what we use to find out the AR and the MA parts of a process. And you may say, okay, but if I have both a process that is generated by an AR part and an MA part, which is what we're going to define now, so the full ARMA process, well, of course, it would be more messy because the two things will show up in the autocorrelation and partial autocorrelation functions, but usually there is one that prevails. So the one that you see more or better than the other one, so you fit that part and then you try to look at the residual of your model to see if there is still some linear memory that you have not fit yet. And so the process is so usually you start, okay, you take your transformation of your time series to make it stationary, and then try to look at the autocorrelation and partial autocorrelation function to identify at least partially an ARMA model, so the AR part, the MA part. You fit the model, you will have a residual. We didn't check the residual last time. So when I say residual, it's the one step ahead errors. Now, in prediction, the residual of the innovation, they're just the one step ahead prediction error, okay? And if there is still memory in those errors, it means that you still have to add some things to your model. So probably you put an AR part, and you're now seeing, there is also an MA part. And I added that to my model. And you go on this way, refitting a new model until you have residuals that are white noise. When your residuals are white noise, it means that, okay, you cannot extract any more linear information from your past to make better prediction of the future. Okay? So that's basically how it works. And in some way, even if you're using nonlinear models, so also machine learning models, you should check also your residuals, at least for zero autocorrelation. I mean, also nonlinear models should produce a residual there white, so white noise. Actually, they even should produce residual that are so-called martingale differences. So not only linear function of the past are excluded, but also nonlinear function of the past are excluded. It means that you're really using all the information from the past. We will see that later. Now we're still sticking to linear models. Okay? So, yeah, we can also, of course, we could simulate from MA process. We can do it really once quickly. It's less interesting than looking at autoregressive processes. But anyway, let's wait. Let's say leave unchanged it. Let's make a new one. So how do I simulate, for example, MA2 process? We can still use the filter function. I don't know, we can One thing I told you, NA processes are always stationary. Okay, we don't have to impose a particular condition on the theta, on the values of the theta. However, they don't have to be unique. It means that I can get always. Suppose I have a solution. We can build something very similar to what we did with MA processes. So actually, if we use the backshift operators, of course, we can write an MAQ model as I take my polynomial operator in B, this time with plus instead of minus. It doesn't really matter much. Okay, and I apply this to the white noise. Okay, and of course I could come up with a characteristic equation. Well, this is usually again shortened in this way. So usually you set this equal to this, and so you can write the process in a compact way this way. And of course I could solve this Q order equation as I did for the AR process. And usually I do concentrate here as well, also only on the solution that are outside the unit circle, but not for the same reason as we did. In autoregressive process, we characterize the stationarity, integration, or even the explosive behavior of the autoregressive process through the solution of this equation, of course, with phi instead of theta. Okay. Here, it's not that interesting, but the problem is that if I find a set of parameters and I put these parameters inside and I solve this equation, I get all the, for example, that some of the solutions are outside and some are inside the unit circle, then there exists a process with the same properties, but with all the solution outside the unit circle. So it's in some way it's not identified. I don't know if you have in mind the concept of statistical identification of a model. A model is identified in statistics usually if you can write, if there is only one parameterization for a given value of the likelihood function. So if a model is not identified, it means that more parameterization brings you to the same result, the same process. Okay. So in some way, an MA process is not unique, meaning that you can have alternative parameterization for the same data generating process. And so for various reasons, one uses also for the MA part only the one solution that has all the roots of this equation outside the unit circle. Also because there is another, let's call it topology, that this process can generate, and when it's got unit roots. We saw the unit root last time for autoregressive process. A unit root process was a non-stationary process. Here we have another type of problem. If we have some solutions that are equal to 1, what we produce is so-called, or any solution which is on the unit circle, it's called a non-invertible process. Is a non-invertible process a problem? It depends. It can make the estimates, for example, very unstable, but it combines badly with the concept of integration and differentiation. I make you just a very simple example. Suppose that we have this process. Okay. It's a MA1, and you may easily check that it's got one unit root. So the solution of that equation, the same equation we saw on Friday, is 1. It's easy, or actually -1. Okay. Well, here 1. So this process is stationary. But it is the difference of a white noise, which is stationary. So suppose this is just a white noise. Okay, this is my process. For some reasons, I get it wrong. I compute the difference of white C. So I suppose it's non-stationary. I was stupid for some way, and I took the difference of that. What I get is exactly that process. So when I integrate this process, so when I build a process which is built like when I integrate WT, so I obtain YT. So it would be like which is still stationary. Okay. So it's kind of it's a strange pathology. It's what, for example, what happens always if I use too many differentiation of a process. You can call it I over differentiate. So if a process is not stationary, and by taking a difference I can make it stationary, it's a good thing. But if a process is stationary and I take a difference, and make it's called non-invertible process that has some computational problems. Okay, so I have to watch out not to differentiate already stationary processes. Otherwise, I will encounter non-invertible process, and usually the algorithms to do the estimation and the prediction will be not working fine in such situation.
So the noise is stationary?
Yeah, I mean. The white noise is stationary. Well, this is also stationary. It's an MA1. All the MA1s are stationary. No. I mean, I told you we could actually solve a similar equation for the MA part. And actually, it matters. We usually do that for identification reasons. And also to rule out possible non-invertibility. Usually this, for example, I think R, but also Python, if you're close to have estimated, or you estimated a non-invertible process, it will give you a message, tells you the process is non-invertible, estimates and forecasts are not that reliable. Okay, so we've also some kind of advice. So usually we want to concentrate on solutions or impose solutions that are all outside the unit circle, also for the NA part, not for the same reason, not to get stationary process. This is always stationary, but it's to eliminate first non-identification. So the fact that I have more than one model that gives actually that birth to the same process, and the second reason is to avoid to get these non-invertible processes that are kind of messy from a computational point of view. Yep.
Could be like deriving a constant function. Deriving a constant function. Then x0, but we'll know what the original function derived was.
Yeah, in some way that's also that's a second problem. It's not this one. Yeah, the second problem is this one. If we have a stationary and invertible ARMA process, we have the real parameters theta and phi, then we can actually estimate in a consistent way the white noise. Okay. So eventually, not at the beginning, at the beginning, of course, we are not able to estimate the white noise. It would be, our estimation of the white noise would be very different than at the beginning of the time series of the real white noise. I can show you why. But then, if we have a stationary inversible ARMA, eventually my estimation of the white noise will converge to the real white noise, which I cannot observe in some way. And so my prediction will use an estimation. Of course, the prediction needs the epsilon if I have an NA part. And so, because if I want to predict the future of y, that depends on the past of the epsilon. I should have some kind of estimate of the past of the epsilon, right? In a non-inversible process, you cannot estimate in a consistent way the epsilon. So it's not identified in some way, as your example about the constant is. So you cannot recover the real epsilon. So that's one of the problems. So that's why usually we exclude so-called non-inversible AMA processes. Those are just problematic. Okay? But anyway, it will be not a big problem. It could be a big problem if you take too many differences. If you apply differences, they could not be there. But sometimes if you take one difference too much, you will probably estimate an MA part which almost cancel that difference in some way. Because you will estimate an MA coefficient that will be very close to -1, and that's also a signal that probably you over differentiated the time series. Okay? So over differentiation could be a problem. Anyway, I wanted just to show you how to simulate one MA process. They're not, as I told you, so interesting as the AR1, the AR processes. So we can, like θ1, we can put, I don't know. I use the same number I used yesterday for the AR part. Actually, I turned them around because the signs are different. Of course, we can use a kappa, so an intercept. So I can put 10, whatever. This is also the mean of the process in this case. How do I simulate it? I can, again, we use filter. This time we will use the so-called convolution filter. So what we need is this one. Again, we can generate normal white noise, a normal white noise process. Again, maybe let's fix also the length of the time series. Let's make it long so so that we have good estimation of the autocorrelation functions. Then we need the filter. Okay, in this case, you have also to place the one, because the moving average or the convolution filter, we take the asymmetric one, but the asymmetric ones want the observation, the last observation, but it was also the contemporaneous observation. So we have to multiply the contemporaneous white noise by 1. And then we get θ1 and θ2. Then we have to pick up the convolution method. And we want one side. Okay. I write all the parameters by name so it's clearer. Of course, we will have 2 less observations than the white noise that are generated, because of course, in order to start the recursion, I need this is an MA2, so I need 2 initial values for the epsilon. So I don't remember if it puts NA or you can check it. Yeah, it puts NA. Okay, so the first two observations are set to missing. Just because I can compute the first MA process from the third one, because it's MA2, so the first two white noise are needed to compute the first observation. Okay? And okay, the plot is not very interesting. I mean, maybe we should look at the first 20 observations. It's actually it's not so interesting as an AR process. It generates less memory, so it's less distinguishable from a white noise, but still is not a white noise. It's got some memory, and the memory we can inquire by using the ACF and PACF functions. So this is the autocorrelation function. In this case, I'm using the one of the package forecast, so I'm not seeing the zero order one correlation, which is just stupid. And indeed, we see that the first and also the second autocorrelation are different than zero, and the other one are pretty close to zero. Okay, this is an MA2, so it's exactly as the theory let us expect. And the partial autocorrelation function instead is gradually going to zero. And here, again, the pattern doesn't have to be very linear. It can also go up and down, can change the sign, whatever. But you have to keep in mind, it goes to zero eventually. Okay? And that's basically, I don't want to simulate more from an MA process because they are not very interesting. Are they useful? Yes, they are useful, especially when we take differences. On real-time series, it's my experience, but I think it's the experience of everybody that's been doing these things for a long time. When you put a difference, it could be non-seasonal or seasonal difference. 95% of the times, you have to put also an MA part, either non-seasonal if you took a non-seasonal difference, or seasonal if you took a seasonal difference. Okay. And why that happens? In some way, it smooths out the effect of the difference. The difference introduces a very rough effect in the time series, and in some way, the MA part tends to smooth that out. And probably real data are smoother than the pure differences, okay? Okay, what if we put the two things together? Then we get the ARMA processes. So I use ARMA models and ARMA process interchangeably. Of course, they are stochastic processes which we use as models. So that's basically it starts with okay. So a generic ARMA process is just, well, with constant. Let's put the constant. You can imagine how it is. It's just putting together the two things. Okay. Which you will see in many situations written as or even sometimes oh, sorry. Well, of course, the mean is, in this case, this is the mean, and in some case, it's just like applying the inverse of this to the constant. So, a couple of comments. Yeah, so it's pretty simple. This is simple as well. Here we just, use the so-called shift operators, so backward shift operators, and the polynomials in those operators, which we already have defined. Keep in mind there's a little bit of a difference between the phi and the theta operator. Here we have negative. So you have minus phi 1, minus phi 2, and so on. And here you have plus theta 1, plus theta 2. In some books, they use negative numbers also for the theta, so the operators are just look like this. They are the same. Doesn't really matter too much. Okay? So you will find these writings in many situations. This is kind of strange because I told you, well, this is not a variable, it's an operator. And this is, of course, a polynomial of operators. So this is the inverse. So if I use the inverse of something, the inverse should exist. Okay. So does an inverse operator, which we can call this way or this way, of an AR operator exist? And the answer, if the process is stationary, it exists. And what does that mean? That actually you can express, so the inverse, so if this this operator, we can use it also using a variable. So if this equation has all roots usually you will read outside the unit circle, which means that all the roots in modulus are greater than 1. This is what we learned last time. So when it's stationary, then there exists the inverse operator, which we can call, I don't know, pi, which is infinite. It's infinite, so it goes on and on, which is the inverse of okay. And of course, we can call this the inverse operator. So what does that mean? It means that actually an autoregressive process has an infinite NA representation. Okay? Because I mean, if I can write, suppose now there is no, let's just suppose there is no MA part. So this is a purely autoregressive process. Well, this is the inverse of the operator, and we saw it's just an infinite operator. It's just like if it were an MA operator, but of infinite Q. Okay? So this means that I can represent an autoregressive process of order P as an infinite movement average process. Okay? Something it's useful. And of course, the coefficient, they all have to, they go to 0 very quickly in an exponential way. So. And it's also true the opposite. So in an invertible MA process, then I can represent it as an infinite autoregressive process. This is less useful. Okay. And you will see all these kind of representations. Let's look at this. Well, in some way, by applying the rules of your normal algebra, you will understand what this makes. This would be like 1 over 1 minus B1B applied to the constant. Okay, but the constant, it's like a time series that never lags, so actually can throw away all the B's. And actually, I get the same formula I showed you yesterday by the direct derivation, or yesterday, Friday, by direct derivation. So the mean is actually equal to, well, K, the constant divided by 1 minus the sum of all the autoregressive coefficients. And this doesn't change even if I have an MA ARMA process. Okay, the only thing that counts for making the constant different than the mean is the AR part. And again, an ARMA process, when is an ARMA process stationary? Well, when the autoregressive part is stationary. Okay. All that counts for the stationarity of an ARMA process is if it's stationary, the AR part, because the MA part is always stationary. Okay. Okay, so, but if you look at this, maybe you feel better. This looks simpler than all the rest, okay? And of course, you said, okay, but this is a strange regression because this part I understand because I can create a lax of the y. The epsilon would be the regression error, but what about this part? And as I told you, in some way, if the process is invertible, then we can estimate the epsilon in some way. Okay, so it becomes in some way a feasible regression. Okay, but is it, yeah. Yeah, this is not what I did here is not very formal, but it works. Okay. As I told you, we have to first prove that the inverse works, and but I mean the algebra. We're lucky. The algebra we all know works also for this operators. So it's not very formal, but it works. Also, in physics, also you have a lot of this situation. There are some people from physics, where like disappear. Some derivative disappears, and the mathematicians will kill them. But it works. Okay, why are ARMA models good models? ARMA processes good models for any stationary process? Because there is a theorem as a result, which is called the Vold decomposition, that tells that well, purely non-deterministic, maybe one day we'll tell you what it means, purely non-deterministic stationary process, they have an ARMA representation. Of course, you have to have a P, a Q, which could be very large, but you can approximate using ARMA PQ models any stationary process, purely non-deterministic stationary process, okay? And so it means that actually, but the real reasons, last time, I think we ended up, or I told you at a certain point during the lessons, linear models are just parsimonious ways to parameterize large covariance matrices. And that's exactly what an ARMA model practically is. In an ARMA models, I have one constant, P phi coefficients, Q theta coefficients. So I have 1 plus p plus q coefficients plus the variance of the white noise. So I have a small number of parameters, but of course, any ARMA models has its own autocovariance function. And so it's like we are parametrizing the autocovariance function, which is an infinite thing. Okay, you could see it as an infinite dimensional matrix, covariance matrix. So, we saw yesterday that in order to produce linear prediction, we need that covariance, right? And that autocovariance matrix is actually very large. If I have many observations, in theory, could be infinite. Okay, and so we need just a way to parameterize that big covariance matrix using few parameters. That's what an ARMA model is a model to use few parameters to approximate very large covariance matrices for prediction purposes. And then we have also this result, which I just mentioned, the bold decomposition theorem that has actually an ARMA model. It's a good approximation to any weakly stationary process. Okay? What time is it? Okay, 5 minutes and we stop. Is the story finished? Not yet. The story is not finished for two reasons. First of all, we need the seasonal part because we left out up to now the seasonal part of the ARMA models. And the second reason is that we could also have so-called Rmax models, where X is like for exogenous variables, so for X variables, for features, whatever you want to call them. So we could use also some known regressors inside an ARMA models. And usually we will be using everything together to make good predictions, especially where we have like high frequency data, where we have a mixture of seasonalities, for example. The ARMA model, in theory, could handle many seasonalities, but the usual ARMA implementation we find in any software just handle one seasonal period, not more than one. So we have in some way to find alternative ways. So what's a seasonal model? I'll try to be quick here. So a seasonal autoregressive process of order large P is just like an autoregressive process. Again, we can have the intercept or not. Usually we use large phi's, which works at multiple of the seasonal periodicity, so seasonal frequency. Or seasonal period, whatever you want to call it. Okay. Okay. And then the white one. So it's just like an autoregressive process. The only thing is that it works just on the seasonal logs. Okay. And of course, the same thing is true for the AMA, seasonal AMA part. Well, actually, the Q should be large Q. Sorry. Okay. And what's a complete ARIMA process? It's that's why it's good to have operators. So in this case, for example, we can define the seasonal AR operator, something like this, for example. And again. It's large. Everything is large here. Because the complete ARMA process is the product of the various operators. So it doesn't really matter if I use first the seasonal, then the non-seasonal, or the opposite, because they commute. So this would be like the non-seasonal one. Then I multiply times the seasonal one. YT. Then I have equal. I can use the constant. And then again, I have non-seasonal MA part. And then the seasonal one applied to the white norm. And finally, because we call them ARIMA models, we add, of course, the need of differences. So the ARIMA P, D, Q, large P, large D, large Q with periodicity S is this model here. Well, use the same ordering. Okay, and it's not finished because we will need also to put some regressor somewhere, but let's start with this, okay? ARIMA, PDQ, PDQ. Now you see everything. Why is there a product? Well, it seems it's not a theoretical thing. It seems that just to work better on real data. The product makes things a little bit odd. We already see that by applying that to the differences. I showed you that if I take the product of two differences, I don't get just the lag two difference. I get something more complex. And of course, the same happens, for example, if we want a seasonal, non-seasonal AR1, so for example, in ARIMA 1, 0, 0, 1, 0, 0, try to build that. So we have the non-seasonal operator, then we have the seasonal operator applied to YT, then, well, okay, the rest is simple. So what happens when I do the product, I get 1, I get phi minus B, I get also big phi B at the S power, and then I get some kind of interaction between the two things. So you see, in some way, I get an extra delay. So if I have the combination of a non-seasonal and a seasonal part, then I also I get the interaction between these two parts. So I get one more seasonal effect, which is, and you say, why is it so strange? But actually, when you apply this to a real-time series, it happens that way. So for empirical reason, I mean, this is good for theoretical reason because it makes the filtering theory much simpler. If you know some, for example, spectral or Fourier transformation theory, these things here make that simpler. But actually, when we go and apply that to real-time series, it seems like that it's necessary to have this kind of interaction between the two parts. It's not just theoretical, also it's good to have it from a theoretical point of view because it makes things simpler, but it's good also from the empirical point of view because usually these things do interact in some way. Okay. So I know today you have to run, so we stop here, and we will be doing a lot of exercises on real data with ARIMA models, because as I told you, this is a very handcraft things to do. It's, of course, you can torture a computer, you can filter a computer how much you want, estimate 1,000 models, and then pick the best one according to some kind of cross-validation of archaic or VIC, whatever you want. But usually, if you can, because if you have too many time series, you can't, a human being can make better models. And the auto ARIMA function of R and also of Python, they're just bad. They don't find nice models or something. Okay, good. Any question?